Okay. Abbiamo già tutti i partecipanti ammessi o ancora no?
Sì, sì, il meeting è aperto.
È già aperto, ok. Quindi in a minute we will begin. Wait just 1 minute. Okay, so shall we start? Stefania? Okay, so the last lecture today will be on standard model by Stefania Gori. I remind you that you can ask questions. I encourage you to ask questions by raising your hand rather than in the, you can also do it in the chat, of course, but I'd rather have the hand raised because in the chat there are several comments and I may lose one question. All right, whenever you want, Stefania.
Okay, thanks. So welcome back, everybody. And yeah, today, as I was anticipating yesterday, the main topic will be the electroweak Lagrangian of the standard model. So we want to understand how that part of the standard model works. And before getting into this main topic, let me discuss briefly a little bit of leftovers from from yesterday. So I wanted to introduce briefly natural units and dimensional analysis, because this is something that we'll use later on, especially when we start discussing more the phenomenology of the standard model. So this is gonna, oops, sorry. This is going to be our section 1.3. So again, natural units and dimensional analysis. So as you have probably already seen, so the idea is that in high energy physics there are some sorry, some fundamental constants that we put equal to 1. So what we do is to impose to say that the speed of light is equal to 1, as well as the reduced Planck constant, so h bar is equal to 1. Now, we know also that you know, the speed of light, the dimensions if you use, for example, the International System of Units, this is a length over time, and instead for h bar, here we have a energy times time, or equivalently a mass times length square times time to the minus 1. So from here we see that we have a relation between length, time, and mass, and we can express everything in terms of a power of energy. So basically, from here we gather that the mass is nothing else than length to the minus 1, and also t to the minus 1, and this is also equal to energy. So when we try to estimate things in high energy physics, at the end of the day, we want to have, we perform a lot of dimensional analysis to see how things scale as a power of the energy. So energy to some power is equal to our physical quantity. So that, okay. And so what is you know, we can look everywhere in the web or in our books and see what is the value for the speed of light and for the reduced Planck constant in whatever units, and then you get relations. So one relation that is quite useful, that is used a lot of times in phenomenology, is to remember actually that h bar c is equal to 200 MeV times a femtobar. Sorry, a femtometer, not a femtobar. And then also it's useful to remember that 1 EV is very roughly speaking equal to 10 to the 15 seconds to the -1, and also very roughly 10 to the 7 meters to the -1. Okay, and this is you know, coming directly from imposing that c is equal to 1 and h bar is equal to 1. Okay. And then, of course, you know, once that you have EV, then you can express every form of energy in terms of seconds to the -1 or meters to the -1. For example, you can express joules into these different type of units. Okay. Now, for dimensional analysis, so this is natural units. So dimensional analysis. And we'll see an example of this, of the power of dimensional analysis later when we'll introduce the weak Lagrangian. It is very useful to see what several quantities, including the fields that we introduced yesterday, what is the dimension of these quantities. So first, the starting point, if you want, is to understand what is the dimension of the action. So notice that whenever I put this parenthesis means that I want to investigate the dimension of some physical quantity. So what is the dimension of the action? Can anyone tell me, maybe? In the chat? Or...
See, I need to unmute if someone wants to.
Oh, okay, maybe I should
speak.
not.
Ecco, no, we have an answer in the chat.
Okay, great. Yeah, so this is dimensionless. That's why I put it. This is equal to 0. Or if you want, you know, I can put. Yeah, let's put this equal to 0. So dimensionless. And if it is not obvious, no, we can think that what is the action, right? So, or what is the Planck constant? So the Planck constant is the elementary quantum of action, and we have imposed that the reduced Planck constant is equal to 1, so it doesn't have dimensions, and that's why the action is also dimensionless. And then from here we can extract everything if you want, because we know that the action, we have introduced it yesterday at the very beginning, is simply the integral of the Lagrangian in 4 dimensions. And then from here we gather that the Lagrangian has dimension 4, so is an energy to the 4th power. Energy to the 4th power. And then here let's play a little bit around with fields. So what is the dimension of fields? So we can do the exercise for scalars. So we can remember, for example, that one term, one allowed term in our Lagrangian for example, for a real scalar that we have seen yesterday was of this type, the mu phi, and okay, there was some factor of 2 for a real scalar, doesn't matter. Then we know that the derivative is equal to this quantity here, and therefore it has the dimension of 1. So this is 1 over length, and therefore energy. We know also that the Lagrangian has dimension 4, and then putting everything together, we get that the dimension of a scalar is also equal to 1. Okay. And then is exactly the same exercise for fermions and gauge bosons. So we have just to remember or to know how to write down some terms of the Lagrangian, and then from the dimension of the Lagrangian we get the dimension of the field. So fermions, we had the term of the Lagrangian that looked like this, as we have seen yesterday. And then from here again, we have a derivative. We have learned what is the dimension of the derivative. And then putting things together, we learned that the dimension of this fermion field is equal to 3/2. And then the last one is a gauge boson. Again, we have the Lagrangian. This is given by -1/4 f mu nu, where f mu nu was given by the derivative minus this other derivative. And then again, we get that the dimension of a gauge boson is equal to 1. Okay. So you might wonder why is this useful? Why is it useful? So there are several reasons. This natural units and dimensional analysis can allow you to perform estimates of physical quantities quite easily. So estimate of physical quantities. Just to anticipate what we'll see later, so what we'll do is to estimate actually the width. I will explain obviously much more later, but we'll estimate the width of a muon based on dimensional analysis. So that's pretty useful if you don't want to enter into the tiny details of calculation, but just to have a rough estimate of whatever physical quantity that you want to compute. And then also it allows you to understand what are the operators that we can put in a Lagrangian. So what operator in a Lagrangian. Because we mentioned that we want to have for example, a standard model Lagrangian, but also if you think about a BSM UV complete Lagrangian that is renormalizable. And this tells you that the dimension of each operator should be at most equal to 4. So dimension smaller or equal to 4. And then having the dimensions of the fields, of course, show you what operator you can write down and what you cannot. Now, so we saw what are the dimensions of the fields, and then we can just write down the dimensions of other physical quantities, as for example, cross sections. So if you take a cross section, so this is an area. This is what a cross section is. You can think about it as the area of the target, very broadly speaking. And so this is an area, and therefore this is equal to -2. So length to the second power, or energy to the -2. Then we have the lifetime of a particle that I denote with tau. This is time, and therefore in terms of energy to some power, we have energy to the -1. And then finally with the width of a particle, that is the inverse of the lifetime. And obviously, I mean, I'm writing a little bit sloppy, but hopefully this notation doesn't confuse you. Well, should probably put the parentheses in this way. And this is equal to 1, okay? And the use this relation when we want to estimate this, the width of the muon later on today, okay? So this is just a little bit of reminders of, as I said, the natural units and dimensional analysis, and then now we're ready to enter into the main topic and to start the discussion on the main topic of today, namely the electroweak Lagrangian of the Standard Model. I don't know if there are any questions on this reminder. Otherwise, we are ready to move. Okay, so since there are no questions, so let me start. Let's write here. So the goal of today. So we want to write and understand the electroweak Lagrangian of the Standard Model. Okay. And then for tomorrow, we'll break the electroweak symmetry and we'll speak quite a bit about the Higgs boson. That's the goal for today and tomorrow. So for doing so, let me first speak a little bit more about symmetries. We introduced some of them yesterday, but I want to discuss with you a little bit more about symmetries. So in particular, we are going to focus for now on a SUN group, a SUN Lie group. So this is a special unitary group, and this is a group that a group of transformations among the components of a complex and dimensional vector. So if you take phi being a n-dimensional vector, a complex vector, then SUN leaves the norm invariant. So invariant. So you will have that if you do a transformation on this field, a SUN transformation, this is simply equal to your starting point. Okay. Now, the reason that I am mentioning SUN is that actually we have this type of symmetry to describe the electroweak interactions. So in particular, we have to introduce what we call a gauge or a local symmetry. So this is a symmetry, or let me say a transformation that depends on space-time, on X. And so if we focus on a local SUN symmetry, and we apply to this vector phi that I introduced before, what happens to phi? So phi will transform as ux phi, or I can write this transformation explicitly, this unitary transformation explicitly, as the exponent of I alpha A of x T of A phi. Let's see what these symbols mean. So first of all, here, as you see, I have some parameter, some continuous parameter that does depend on X, and that's why we're considering local transformations. And these are what we call the generators of, in this case, SUN. To be a little bit more precise, and this is a note for a little bit more for experts, I should put here an R in the sense that these generators will depend on the particular representation of the group that I'm taking. So phi can transform in many different ways under the SUN group. We'll focus on the low dimensional representations of SUN, but in principle, you can write down as complicated representation as you want, and then you will have different type of generators of this symmetry. Okay. And then what you see here also, I'm putting an index A that tell us that indeed we'll have more than one generator. In particular, we'll have, for SUN, we'll have n square minus 1 generators. So the index A will go from 1 to n square minus 1. Just to introduce a little bit of symbols, because we'll use them later. So these generators of SUN will obey the Lie algebra, namely some computational relations. So we'll have that the commutation between TA and TB is equal to I FABC TC, where these F are structure constants. Okay.
Stefania, can I read a question from the chat?
Yeah.
So the question from Ankita Kakoti. You have written gauge or local symmetry. Gauge symmetry can be global too, right?
What I mean with a gauge symmetry is a local symmetry that does depend on the space-time. So it's not a global symmetry. These are two different things. Yeah.
Thanks on behalf.
Okay, very good. Okay, so this is just a very generic introduction about SUN transformations, local transformations. And then we can be a little bit more specific and connect these to the electroweak symmetry. So if you think about electromagnetism, so what we know is that electromagnetism is related to a U1 local transformation. That is a very special case, so it's a simple case, just rotations. And for a U1, if you have something that is transforming under this U1 local transformation, then your generators are simply identity matrices. For phi that is charged under U1. So for example, if you take, I don't know, an electron that has an electric charge, the electron will transform, in this way here, where you have the exponent of your charge, but here you have something trivial that are the that is simply an identity matrix. Or so let's write it explicitly. So for an electron, or let's write for whatever fermion with a charge, fermion with a charge Q, this fermion will transform in the following way: e to the I Q. Then you have these continuous parameters. Let me put them here: alpha of x, and then phi. Okay. So this is a direct consequence of what we saw before. But then we end up having a problem. So let's recall the Lagrangian that we have seen yesterday for a fermion. So yesterday we wrote, we wrote that we have terms like this for a fermion. But then we can see what happens to the Lagrangian if we do this U1 local transformation. Let me, just for simplicity, let me call this Q of X, just for a matter of simplicity to write it down. So let's do a U1 transformation to the Lagrangian. So here we'll get e to the minus I Q of X. Then we have I gamma mu. Then we have e to the I Q of X, the derivative applied to the field. But then we have also a second term because so this guy here will transform as we have seen, Q of X psi, but then we have this derivative that is acting on both of these terms, where both the field and this exponent depend on X. So here we'll have two terms. And then here again, I have psi e to the I Q of X. Okay. But then you see what is the problem, that even if you simplify this expression, so there will be terms that go away. So this exponent will go away. And of course, I should not forget that I have also mass term, but nothing happens to it. But you see that we have this extra term. So what this little exercise is telling us is that if we just take the Lagrangian that we've seen yesterday, this Lagrangian is not invariant under a local U1 symmetry, okay? And I think someone asked me yesterday, if I remember correctly, but so here what we are trying to do is to write down a Lagrangian that is invariant under the symmetries that we are imposing. And here I'm imposing a local U1 symmetry. So what I want to have is that is a Lagrangian that is invariant under U1. So there is something that I need to do on top of the Lagrangian that we introduced yesterday.
Stefania, someone asks if Q of X can be complex.
So this, let's see. No, so these are real continuous parameters. And then these, so I should have said, and these generators are actually Hermitian. So the idea is that this U transformation is a unitary transformation, and then, yeah. Okay. Okay, excellent. So we need to do something, and what we do is, so what to do is to replace this derivative with what we call a covariant derivative. So basically, we need to introduce gauge fields in order to have a Lagrangian that is symmetric. So introduce gauge fields. We put S in parentheses. In this case, we just have to introduce one gauge field that is the photon. So the covariant derivative will be defined as the partial derivative plus I Q A mu, where this is the photon that we know. And notice that, just not to get confused, this Q here is simply this Q here, is the charge, for example, of the electron. And but this is not the only thing we need to do. What we also need to do is to specify the property of transformation of this photon under the local U1. And so the photon will transform in the following way as A mu minus the derivative of alpha of X, where again, alpha of X were the continuous parameters that we saw above here. Okay. And so a little exercise, so if you want at home, we can check that the Lagrangian, that is written as psi I gamma mu d mu minus m psi, is now invariant under this U1 local symmetry. And actually, I can even add an additional term, namely the kinetic term of the photon, so this f mu nu, and then again, we can see that the full Lagrangian is invariant. Okay. So we found, we wrote down all the possible terms of our so our EM Lagrangian that are invariant under this local U1 symmetry. Okay, so this is our QED Lagrangian.
Question from Gautam: one of the Q term in A mu field as in the gauge transformation, I guess. Gautam, do you want to speak yourself?
Hey, Stefania.
Hey.
I was wondering, so in the transformation for the A mu field under U1 for the photon, will we not have a 1 over Q term for the?
Oh, very good. It depends how you. It depends how you define it. So using the definition that I have, you don't have. Sometimes, let's see. Sometimes
because
in books,
we have an IQ A nu in the covariant derivative, so I'm just assuming we have 1 over Q.
Right. Yeah, but actually you can check that with the notation that I'm using, you don't need it. So if you consider the transformation I'm writing above here as e to the I alpha x, then you need to put this q, this 1 over q. But it depends. I mean, you can shuffle q's around as long as you are self-consistent is all fine. But it's true, in some books you find that here you have 1 over q. Not with the notation that I'm using. I think the notation I'm using is self-consistent.
Okay.
Yeah. Okay, very good. So this is obviously the simplest example, but this is you know, a very important example because it is describing our QED. And then notice that because of you know, this local symmetry, we have introduced a interaction term between 2 fermions and 1 gauge boson, okay, and then the photon. Then we can generalize this to the weak interactions. So this was electromagnetism, and then we can do the same, I mean, a similar thing for weak interactions. This will correspond to a SU2 local gauge symmetry. And then we have to play the same game, basically, just that we have to be quite more careful because this is a non-abelian gauge symmetry, meaning that the generators are not commuting, non-abelian. But in terms of...
sorry, Stefania, before you go to the non-abelian, would you like to answer another couple of questions? One from Mandeep, who asks why we want our Lagrangian to be invariant under local gauge transformations.
Yeah, so this is the way I present it is that we are imposing a U1 local symmetry, and then I want to have you know, a system and a Lagrangian that is invariant if I do those type of transformations. Now, at the end of the day, what we are trying to do is to describe the interactions between fermions that have an electric charge and the photon. And then this is well described by a Lagrangian that has this U1 local symmetry. Okay, but that's the goal. Describe you know, the interactions between fermions and photons. Yeah.
And there's another one from Ankita. I'm not sure. Can we define coupling constant in this context? Maybe Ankita, you want to?
Hello, ma'am.
Hi. Yeah,
ma'am, as you have written, when we introduce the gauge fields, so that is the covariant derivative is equal to del mu plus IQAR, that is the photon field.
Mm-hmm.
So can we define, ma'am, the coupling constant in this context?
Yeah, that's right. So this Q will be my coupling constant. So you can think, if you think about an electron here, you will have just the electric charge, and this is telling you indeed how strong is the interaction between your electron and the photon. Yeah, that's right. Does it answer to your question? Okay. Okay, very good. So for the weak interactions, these are well described by an SU2 local symmetry, and then we have to understand what are the generators. TA. We have learned at the beginning that we have n square minus 1 generator for SUN. So in this case, we expect to have 3 generators. For this SU2, and these are actually for the fundamental representation of the group. These are the Pauli matrices, sigma of A, and actually, yeah, typically people use a different normalization, so there is 1/2 here. It doesn't really matter too much. And then we do the same thing, so we can check that the Lagrangian wouldn't be invariant under SU2 if you don't do anything, so you have to introduce a covariant derivative, and that is defined as the partial derivative plus IG, and this again is my coupling constant, as we were discussing before, for electromagnetism. Mu, let's write explicitly, and then TA times psi. And then now these gauge bosons here. So we have 3 gauge bosons, because notice that here we have an index A that goes from 1 to 3. So these, as we will see tomorrow, they will correspond to, let's write them as, well, they will generate the W and the Z boson of the standard model. Not exactly, we'll see all the story tomorrow. And then how do they transform under the SU2? So let me define a mu as mu A TA, this combination, and this transforms as U A mu U to the minus 1 plus I over G derivative U to the minus 1, where U was the thing that we were defining above, namely this thing here. Let's go just a second above. So this was the U transformation. Okay. So, and that's that is what is, these are the transformations and the covariant derivative that allow us to write down a Lagrangian that is invariant under SU2. And then again, our weak Lagrangian looks like before, just that we have a different covariant derivative, d mu minus m psi. Again, at home, you can check that is invariant under SU2. Again, at home. And you might wonder, what about the kinetic term of these gauge bosons? So I would like to also, for the weak gauge bosons, to write down something like this, F mu nu, F mu nu. And this works only if I define F mu nu in a bit different manner if compared to the abelian case. So what I need to do, so this would be, my the field strength in the case of electromagnetism, but now I need to add this extra term that is the commutator between A mu and A nu. And in this way, again, this term here, you can check that is invariant under my SU2 transformations.
Quick question, whether G can have a group label, can be dependent on the generator.
Very good. No, so this is a universal coupling constant that is defining my field. And so for as far as we know so far, the fermions that we have discovered in nature, and then also actually the Higgs boson itself are in fundamental representation of SU2, and basically everybody interacts in the same manner with the gauge bosons. Once that you write this weak Lagrangian as I wrote it down. So this is just a universal coupling, and actually even on top of that, everybody is in fundamental representation.
I wonder if he refers to the different group factors you'll have later on.
Different group factors, not sure what you mean.
Oh, the fact that then you'll have eventually different coupling constants in the standard model, strong.
Oh, sure. So this is obviously only the weak coupling constant that is different from the Q, from the electric charge that is describing electromagnetism, and that is different from the strong coupling constant. So this is, specific for the weak interactions.
Hello, please, Pinak.
Hello, ma'am.
Hey.
Ma'am, what is the physical significance of adding this commutator term in this F mu nu for SU2 local invariance?
Oh, very good. So basically this, you might wonder how, so you have these fields A mu, and they, as you can see from here, they transform in a weird manner, if you want, under SU2. And the reason being that SU2 is non-abelian. So you are dealing with generators that are not commuting. And therefore, what you learn is that also your field strength will have a term that is coming from this, that is directly connected to the fact that the generators are not commuting. Now, in terms of physical interpretation, actually, this is something I wanted to comment on because it's very, very important. So you see that if you plug in this F mu nu in the Lagrangian, contrary to the electromagnetism, what you learn is that you will have extra terms, in the sense that you will have interactions between 3 gauge bosons, and then also between 4 gauge bosons. Okay. So these are new interactions arising in a non-abelian gauge symmetry. And this is obviously very important phenomenologically. This is something that we can check in our experiments, and it was found to be true. And this is, of course, not happening between photons, so photons don't auto-interact. So in these terms, in this sense, this additional term has very important phenomenological consequences. And only thanks to this term, you can write down this kinetic term in a SU2 invariant way.
Thank you, ma'am.
And there's another 2 questions. Maybe we can take them if they are short, otherwise we can defer them later on. Manuel?
Yeah, thank you. Regarding this universal coupling constant, is the reason why we take G and universal coupling constant just due to phenomenology? So we know that Z and W boson interact the same way, or is there a theoretical reason why it has to be universal, so that I cannot say C boson and W boson couple differently?
Yeah, so so let's go back maybe to our, let's see. 1 second, where did I write it down? Yeah, so if you consider a SUN, let's see. Yeah, so we know, let's see. Yeah, so what we are doing is, I wrote it down explicitly here, but for a U1, but is the same also for the others. So what we are doing is to take, let's see, how do I explain this? Yeah, so the bottom line is that we know that actually everybody's interacting the same way with W1, 2, and 3 of the weak interactions. And so this is a universal coupling that we are plugging in these SU2 transformations. Yeah, and so the idea is, I thought I wrote it down, sorry. Yeah, it was here. So the idea is that you are factorizing out from here a universal coupling, and that is the same no matter what A you are taking. Yeah. So, and this is phenomenologically something that has been checked very accurately and found to be true. Yeah.
Okay, thank you.
Mm-hmm.
And there's a last question by...
Thank you. The last is also related. It's just that as in the U1, you see that the charge can depend on the fermion or on the particle that it's interacting. But here we have a charge that it's equal for all the fermions, because as I saw, like when you write the F, the field strength term, we add the charge on there. So it seems that we can't do a charge specific for each fermion.
Yeah, that's true. That's true.
It's true. It has to be universal then because of
that's
that.
Right. That's right. Yeah. 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 As you can see, I'm not specifying. So this is the same G for whatever fermion that is charged under this SU2 gauge symmetry. Yeah. Yeah.
Right. Thank you.
Yeah, of course, I mean, we should not be confused. So tomorrow we'll discuss quite a bit about it, and then it will turn out that, you know, the interactions with the W boson and the Z boson is different, but this is coming from the fact that we are breaking the electroweak symmetry. So, but we'll learn all about it tomorrow. So for now, we have only this universal coupling G with everybody. Yeah. So I think this is actually a good moment, a good time for taking a break. So maybe you can take a 5 minutes break.
All right, perfect. Then we will reconvene at 55.
Yeah.
Okay. Okay, we are ready to resume, but before, can I ask to the technical assistants if they are listening to make me co-host again, because I lost the connection for a moment. Otherwise, I cannot unmute people. Okay, great. Thank you very much. It's fine. Right, so we can continue. Let me see if there are questions. Okay, no, so these are more of comments. So please, if you want to ask questions, I recommend that you raise your hand so I can tell them from comments. Having said that, please, Stefania.
Great. So now it's time to start our chapter 2. So here we want really to go a little bit more into the details of the electroweak Lagrangian. So let's start with a little bit of introduction of why the weak interactions. So why weak interactions? And this is, if you want, a little bit of a historical perspective. And so the reason that historically we introduced the weak interactions is that we had quite a bit of data that we didn't know how to explain in the context of electromagnetism. So several phenomena could not be explained by electromagnetism. And the classic example is beta decay. So the beta decay of atomic nuclei. So beta decay you can write down as you take some whatever element X with some mass number A and atomic number Z. And this will decay to a different element, let me call it X prime, with one more proton, so Z plus 1, and then emitting an electron. Now, actually, we'll comment a little bit on the fact later on that we need to conserve the lepton number. So actually, there is not only an electron coming out, but also an anti-neutrino. And so this is a process that we had plenty of evidence for, with different type of nuclei. At elementary level, I mean, at elementary level, this can be written down as a neutron going to a proton and an electron and the antineutrino, or also, a down quark going to an up quark, an electron and the antineutrino. And obviously, I mean, you cannot write down any, Feynman diagram that can generate this process just using interactions with photons. So we needed something extra on top of electromagnetism. And then the second example that is quite important is actually muon decay. So we knew that muons were decaying, and then we have this decay mode into an electron and then two neutrinos. I mean, an antineutrino and the neutrino for the muon. Okay. So once when you have a lot of data that you cannot explain, then you have to invent some new physics. And the first proposal was coming from Fermi in the 30s. And the idea was to write down hexaterm in the Lagrangian. So the Fermi Lagrangian, let me call it LF, so the Lagrangian that he proposed was of this type, where you have some coupling constant, and then he wrote an interaction term like this, where these are our gamma matrices. here is a proton and a neutron, and then you have here an electron and the neutrino. So you see that this is a sort of a 4 fermion operator. And it has the same structure of the electromagnetic interactions. In the sense that you have a vector coupling, say, for example, between the electron and the neutrino. Okay, you have simply a gamma matrix. And then obviously you can do, something similar for muon decays. So you will have some coupling constant, and then your muon, neutrino, the muon, and then an electron, and your neutrino. Okay, for muon decays. So if you think about it in a Feynman diagrammatic way, you have these 4 fermions coming together. So you have a very, very short range force. Contrary, to electromagnetism, that you have a long range force. Okay, and the strength of this interaction is parameterized by this coupling constant G. And actually, we can see what are the dimensions of this coupling constant. So let's write it down here. So what are the dimensions? So we can use the tools that we saw at the beginning of this class to understand the dimension of this coupling constant. Can anyone maybe write it or tell me? See. So what is the dimension of this G? Okay, minus 2.
Minus 2.
Very good. Yeah. So the dimension is minus 2, so 1 over mass square. And I was asking this because actually here is a little exercise that we can do using dimensional analysis to see how to give an estimate of these quantities, as for example the width of the muon that is decaying. So using dimensional analysis, what we expect is that the width for a muon to decay to an electron and the 2 neutrinos will be proportional to G square, so the coupling constant square. This will give us 1 over the mass to the 4th power. We know that the width is equal to an energy in terms of dimensions, and then we need to put here a mass to the 5th power, right? And we expect that to be the mass of the muon. And actually, yeah, this give us a relatively good estimate of the width. If you do it correctly, actually, you get quite a bit of suppression if compared to this, because you have some powers of pi, and you have a big number here in front. But okay, I mean, the dimensional analysis give us the right scaling at the leading order for this width. And actually, interestingly enough, is that this coupling G, the measurement of this coupling G is extracted from the measurement of the muon lifetime. So measurement of muon lifetime is telling us is giving us a determination of G. Determination of G. Okay. So for the people who are used to work with a Fermi constant, that is usually denoted as GF, this is basically the G that I am writing down there, apart from subfactors of 2, but okay, just for completeness. Okay. So this is what Fermi guessed in order to explain this data for beta decay. But then there were two problems on this. So the first problem, problem of Fermi interactions. So the first problem is that, so take the Lagrangian for the muon decay as an example. So we wrote it down again as this way. And then what you can do is to split your fermions in terms of left-handed and right-handed fermions. So, for example, E, you can write it down as P left E plus P right E, where these are the left-handed and right-handed projectors that we introduced yesterday. And then you can do the same thing also for all the other fermions. So at the end of the day, if you do this exercise, you will find several terms in this Lagrangian. So you will find a term like this, where you have a P left here, and another P left here. But then you have also a term where you have both P right and then the other combinations, right? So you have all the combinations of left and right fermions. And this is, again, coming from the fact that the structure, the Lorentz structure that Fermi guessed was the same structure as for electromagnetism. So this vector interaction just with a gamma matrix, if you want. But then there were studies of beta decay of several nuclei, as for example cobalt, by Wu in 57. So the cobalt was, for completeness, was decaying to nickel and then an electron and an antineutrino. And basically studying the direction of this electron, it was found that this direction had a preferred, so the electrons were having a preferred direction. And this was actually not consistent with the vector structure of these interactions. So not consistent with, let me write for, to be brief, with this gamma mu type of interactions. Okay. So it turned out, so the conclusion of all these measurements was that only right-handed antineutrinos and left-handed electrons were participating to the process. Okay. That's why, yesterday I was quite a bit, speaking about chirality and so on. And here we see that indeed, to describe this data for beta decay, we had some special combinations of electrons and neutrinos. So at the end of the day, if we want to write down properly this would-be Fermi Lagrangian, we should write it as in the following way. So you have again a gamma alpha, but here you put the left projector, and there you have a muon, and then the same thing for an electron. Of course, I mean, I should always add the emission conjugate, but okay. So this is something that is much more consistent with data. And as you see, we have only a left-handed muon or neutrino here participating, and correspondingly, this guy here is right-handed, okay, for the antineutrino. So in this sense, you might have heard that we say that the weak interactions are V minus A type of interactions. So weak interactions, V minus A, right, because this is a gamma alpha, and here you have 1 minus gamma 5 over 2. So this is the structure for our weak interactions. And what is interesting is, and this is something that we could check at home again, is that these interactions here break parity. So they are not invariant under parity transformations. Okay. So again, this is a 4 fermion type of interaction, but now instead of having simply this gamma mu type of structure, you have a gamma mu p left and then another gamma mu p left. Okay. Now, we are still not 100% satisfied. So this was the first problem, and the second problem being that this is an effective interaction. So you see that, so if you look at just the operator that I wrote down, so this operator here, so this operator has dimension equal to 6. That's why we said that the coupling constant G had the dimension -2. So this is a non-renormalizable operator, and actually is very badly behaved in the UV for certain processes. So one can show that if you take some other process like, I don't know, the scattering of an electron and a neutrino to give, for example, a muon and another neutrino. These, again, we receive a contribution from the operator that we wrote above. But then you can compute a cross-section using that effective Lagrangian. So the cross-section for this process. And what you're going to see is that the cross-section will be proportional to this coupling strength G square. But now you have times S, where S is the center of mass energy. And you see that in principle, you can imagine doing this experiment at higher and higher energies, and at a certain point, you know, if you want it in the limit, this goes to infinity. So in this sense, this theory is not well behaved, and what we say for the aspect is that we are breaking perturbative unitarity. So we don't like this type of Lagrangian, and but interestingly enough, this is a sort of a low energy description of our weak interactions. So if you want the correct description of the effective Fermi Lagrangian, is indeed using the Lagrangian that we saw earlier today for the weak interactions, where you have this SU2 local symmetry, and then you can write down, you know, using delta Lagrangian and the Feynman rules that you extract from there. You can write down a Feynman diagram like this, for example, for muon decay. So for muon decay, you have a muon coming in, you have your antineutrino, you have another antineutrino here and an electron, and here you're putting your W boson. And interestingly enough, if you integrate out the W boson, so if you think about it as being heavy compared to any other energy of the system, you get your effective interaction that I denote with a dot. With G, so the coupling constant that we saw above, that will be basically equal to the G of SU2 over the mass of the W square. And actually, the range of the weak interactions is short. So this is a very important difference if compared to electromagnetism. And this tells us that actually the W boson has to be heavy. Okay. Okay. So at the end of the day, so what did we learn here? We learned that the SU2 gauge symmetry that we used, that we introduced above, is the the local symmetry that is allowing us to describe the weak interactions. But also we have learned that only some of the fermions are participating to these weak interactions, namely the left-handed fermions, or correspondingly the right-handed antifermions. Okay. Now we can really write down the weak Lagrangian. A little bit more explicitly compared to before. Namely, we'll have a sum over all fermions of the standard model. Then we have this I, gamma mu, d mu, so the covariant derivative that we introduced before. And then we have the part for the several gauge bosons, namely we have 1 minus 1 over 4, sorry, F mu nu. But now, this is actually exactly the same Lagrangian that we brought above, but the difference being that we have learned that this d mu plus IG, I think we call it A again, so A mu, A T A of psi I. And we learned that these generators, so T A of psi I, are equal to 0 for right-handed fermions. Otherwise, these are equal to our Pauli matrices, again over 2, for left-handed fermions.
If I may interrupt, Stefan, there's a question from Mandip related to what you said before. What do you mean by integrating out the W boson?
Yeah, so it is true, I didn't really explain this point. So the idea is, so say that I give you this Feynman diagram to compute, and then you can use your Feynman rules to compute the width, in this case for the neutrino decay, right? Now, what we can do is to match this width to the width that we would obtain from the Fermi Lagrangian that we saw above here, where I'm putting the arrow. In the sense that, again, so you can do this calculation here from the Feynman diagram, but you can also calculate the width simply starting from this 4 fermion Lagrangian, okay? And then you get 2 different answers. Now, when you want to match the two, you say that basically the physics that the physics that is described is the same, and then you compare the 2 results, and then you get this sort of matching condition. Now, whenever you write down a Lagrangian of this type, the idea is that the interaction is super short range. That's why you can write down this point interaction, so this 4 fermion interaction. And short range means that you have something like the W boson that is very heavy. Otherwise, you cannot write down a 4-point interaction in this case. So in this sense, you are integrating it out with the idea of having a W boson that is much heavier than any other physical scale that is involved in the process. In the process. Okay, and this, I mean, is I introduced this in terms of the Fermi theory, but this is something that you do every time you have to deal with effective field theory, where in effective field theory you have operators with a dimension that is bigger than 4, and then you do this type of you can do this type of matching. I hope it explains a little bit the thing, but I agree it's a little bit rushed. I mean, one can talk a lot about what it means to integrate out particles and write down effective field theory, but hopefully it clarifies a little bit this point. Are there other questions? Or?
No, not for the time being.
Okay, great. So this is what we have learned more doing this sort of Fermi exercise if compared to before. And then I think to complete today the discussion of these electroweak interactions, we can write down what are the standard model fermion representations. So we have learned that to describe the electroweak interactions, electroweak, we have this SU2 times U1 group. And actually, and this connects to the class of tomorrow. So this is the SU2 of the weak interactions, but this is not a U1 of electromagnetism, but this is called hypercharge. For now, you can think about it as some different U1, and we'll see tomorrow that this is actually connected to the electromagnetism, but it's not exactly the same thing. But obviously, I can apply the same rules of a U1 gauge symmetry that we have learned earlier today. And this will be associated to a covariant derivative. Let's write it again. Let me use W this time. It's easier. Plus I. Again, I have another universal coupling that I call G prime. And then I have B mu. So this is the gauge boson for the hypercharge gauge boson, and these are the several hypercharges of the several fermions. And then let's see what are the several representations that we know about. So you have quarks, you have up quarks that are right-handed, and so they transform as a singlet under SU2 because we have learned that they don't communicate to the weak interactions. So you see here that the generators will be simply equal to 0, so there is no transformation, it's a trivial transformation. And then the hypercharge will be equal to 2/3. Then we have down quarks, 1 minus 1/3. Again, they don't transform under SU2. And then we have left-handed quarks. These are doublets under SU2, so this is the fundamental representation of SU2, transforming with Pauli matrices, then 1/6. And then it's useful, and especially for the discussion of tomorrow, to think about it in two components, as U left and D left. Please don't get confused. So I don't mean this being, you know, by spinors or so. So these are two different fields, and I'm writing explicitly the SU2 components. Okay. So these are the representations that we know of for quarks. And then we have leptons. We'll have ER 1 minus 1. And then we have the left-handed leptons. These are a doublet, and then minus 1/2. And then again, I can write down the two components as the neutrinos and the charged leptons. And then, you know, in principle, we could put some indexes here in I everywhere, meaning that I equal to 1, 2, 3, and this is an index of flavor, because we know that we have 3 generations for each quark and lepton of the standard model. And the question is, so several of you might do some research on stellar neutrinos. We don't know if they exist. I would say most probably, but if they exist, these stellar neutrinos, let me write them as NRI, this will be simply a singlet representation. So they're singlet under SU2, and also they don't have any hypercharge. Okay. Obviously, I mean, this tells us basically everything about the standard model before electroweak symmetry breaking. For completeness, I should mention that, you know, we should not forget that we have also another group that is SU3 of color for the strong interactions. So I want to discuss this during these classes, but it's if you understand SU2, SU3 is very similar, broadly speaking, very broadly speaking, and you can play the same game of covariant derivative and so on. And then what you learn is that the quarks are in the fundamental representation of SU3. So these are triplets under SU3. That's why we know that you have you know, different color, 3 different colors for the quarks. And then during this school, you will have lectures about QCD by Cacciari, so you will learn a lot more. And to connect to what we will see tomorrow, you might wonder what about this hypercharge. And I can tell you already that what we will learn tomorrow is that the electric charge that we are familiar with is a combination of this hypercharge, so Y that you see here, plus the third component of the isospin, so the third component of SU2. Okay. Yeah, so this is basically all I wanted to say about the electroweak interactions. And also one message that I wanted to give from here is that we have learned that all these interactions are simply described. So the electroweak interactions are fully described by 2 coupling constants. And yeah, if we use this hypercharge coupling here, oops, sorry. What we have are the G and G prime coupling constants. And once we know that, we know basically everything about the electroweak Lagrangian of the standard model, since we have specified what representations we are plugging in. Okay. And tomorrow we want to understand indeed the origin of this relation here, so why we introduce hypercharge, and then we want to understand the electroweak symmetry breaking and a little bit of phenomenology of the Higgs boson. Okay, so we are done, and now let's start with more questions.
Right, thank you very much, Stefania.